Well, hello. Today we're going to continue talking about our probabilities unit. We're going to talk about more about the counting principle and something called permutations. These deal with permutations, combinations, ways of counting things. And so we're going to learn some new notation today. And we're also going to look at our calculators, and we're going to use something called NPR. So we talked previously about the counting principle, and specifically we looked at how many different lunch combinations could we do. We saw how a tree diagram is a great way of visualizing how the counting principle looks. And it just means that if you have m distinct ways of doing one thing and n distinct ways of doing another, then you would have m times n ways of doing that. So let's go ahead and look at how we might use that to figure out some license plate problems. A license plate is made up of 6 uppercase letters or digits. The first 3 positions are letters and the last 3 positions are digits. How many different license plates are possible? So the first thing I'm going to do is I'm going to put down 6 blanks. And the thing is that we know that the first 3 positions are letters, right? And then the last 3 positions are digits. So that's these here. And we have to think about how many different letters are possible. And on a license plate, can you repeat letters or digits? Well, it sure doesn't say that we can't. It doesn't say no repetition allowed. And it makes sense that we could feasibly repeat them, so I think we probably should. So we would ask ourselves, how many letters are there in the alphabet? Well, there's 26 letters in the alphabet. And since we can repeat them, for the first blank, we would have 26 choices for a letter, right? Anything from A through Z. For the second blank, we have 26 choices for a letter and also 26 choices for a letter there as well. Because we could repeat them, this could be AAA, right? It could be AAB, AAC. And it doesn't have to be AA. It could be like ZXY, right? Or XYZ. Those are all different. Okay. Now let's move on to the digits. Now a lot of people think of the digits, they think of only 9 of them, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. But remember that 0 is also a digit. So how many different digits are possible in this first place? 10. And then, well, we can repeat them, which means it'll be 10 and 10. And then what we're going to do is actually just multiply all these together. So I've got here a TI calculator. Let's go ahead and take a look at this one. So we'll do, we'll turn it on first, I guess. Maybe we won't use a TI. There we go. Okay. So 26 times 26, I could just do to the third power, times 26, and then times 10, times 10, times 10. There we go. Now if we check our commas here, this gets us 17,576,000. There. This is how many possible plates are permitted to be printed. All right? If we don't have any other restrictions, if we're allowed to repeat things, if every possible combination is allowed. Right? And there are some plates that they just don't allow, maybe because of, for certain reasons. But so then there's not actually 17 million plates, but under this particular scheme where we don't have any restrictions, it's just 26 times 26 times 26 times 10 times 10 times 10. That's it. That's it. Okay, and that's called the counting principle. This problem, we are going to think about how many ways we can line up 8 books on a shelf. Like maybe you have your 8 favorite books, right? But your shelf, you only have room to display 4 of them. So if we only have room for 4 of them, I'm just going to put 4 blanks. Imagine a shelf and you've got just 4 places to put books. But you look down here and in your pile, you have all these books, right? You've got 8 of them, 8 books down here in a pile, and you can only fit 4 of them on the shelf. So when you look at this, how many different books could you reasonably put here in the first spot? Well, you can only fit one book there. I know, I get that. But you have 8 choices for your books. So 8 different books could go in the first place. Then, once you put a book in that spot, you can't put the same book over in the second spot. That wouldn't make any sense. So in this case, maybe you put, maybe Harry Potter volume 7 is your favorite. So you put it there. Now you look down, and now you only have the first 6 Harry Potters along with Fantastic Beasts. I don't know, I think that was one of the books. I didn't read it. So you only have 7 more books to choose from. So once you pick, maybe Harry Potter Volume 2 was your favorite. So then you would put that here. You had 7 choices, and now you've put that there. Now you've put 2 books up on the shelf. You can't put either one of those books again, so you're going to decrease by 1 each time and decrease by 1. Right? Because once you put a book in a spot, you can't put it in another spot as well. And so then what we have is just 8 times 7 times 6 times 5. Right? So let's go ahead and we'll go to the calculator. We'll do this on a calculator because it's just much easier that way. And we'll do 8 times 7 times 6 times 5. There we go. 1,680. That's how many different possible ways you could arrange 4 books if you have 8 to choose from. Okay? This is just the counting principle, and we'll learn that we could actually use something called a permutation. We'll learn about what that looks like in a little bit. At Old Navy, a supply of solid colored t-shirts has just arrived. They love their solid colored tees there. And the colors are green, blue, white, yellow, and red. Now Billy, the manager, decides that he's going to display each of them on a shelf. How many different ways can he display the 5 shirts on a shelf? Okay, so we're going to display all 5 colors. All right. And we have to decide how many different choices do we have for the first spot. Well, we have all 5 colors, and any one of them can go there. So we have 5 choices for the first spot. Then, once you pick a color, maybe blue. Okay, so he picks blue and he puts that one first. Now we only have 4 colors to choose from for the next spot. So maybe for that one he picked red. Then we only have 1, 2, 3 colors left for the next one. Maybe he picked white for the middle. And then he picks green. And then now he only has 1 choice left for this last one. So we're going to do 5 times 4 times 3 times 2 times 1. Let's see, 20, 60, 120. There's 120 ways that he could arrange those 5 shirts. Seems like a lot, right? But that's how the numbers come out. Now this time, he has decided, Billy's decided as the manager, he has this power apparently, and he can choose that he wants to put the blue t-shirts in the middle. This one is locked in. This one is going to be blue. So if you think about this, how many choices does he have? He only has 1 choice here. It's blue. That's it. Just 1 choice. Okay, so blue is taken care of. Now let's go back and decide how many different colored shirts could he put in this spot. Well, he already took care of blue, so he has the other 4 colors left to do there. Right? And then he'll have 3 colors, and then 2 colors, and then 1 color. Okay? So if blue must be in the middle, then he actually only has 24 ways of arranging these shirts. That cuts it down pretty quickly. All right, the last one. Billy he's changed his mind, and he wants the white t-shirt to be the first and the blue one to be the last. So this one right here is guaranteed to be white, and this one is guaranteed to be blue. Apparently he didn't like blue in the middle. Now, if this one has to be white, then that means there's only 1 choice there. Has to be white. If the last one has to be blue, there's only 1 choice there. And if you think about this, like how many choices we have left now, well, we've taken care of the blue one, we've taken care of the white one. That leaves us green, yellow, and red left for these other three spots. We could have any one of those three choices for this one. And once you pick one of the colors, maybe it was green. Once you pick that, now all we have left are yellow and red to choose from. Now we only have two more to choose from. Maybe he picks yellow. Now he only has one choice. This is it. Red is the only shirt that could possibly go here, is what we're thinking, if he had picked, the colors in this order. So by locking up a couple of those, you can see we reduce the number of possibilities pretty quickly. 3 times 2 times 1 times 1 times 1 is just 6. So there are only 6 ways that he could arrange those if white has to be first and blue has to be next. All right, this is a good one to try on your own. Now I think you're probably getting the hang of this. Put down the number of blanks and decide how many how many possible values they could fit in there, right? But here we go. If you haven't paused it and you're just waiting for me, that's fine too, I guess. A password is used to gain access to a computer, and it consists of 2 lowercase letters followed by 4 digits. So we've got 2 letters and then 4 digits. Now, notice it's kind of important it says lowercase letters. That's because if they didn't make that distinction, oftentimes passwords are case sensitive, meaning a capital A is different than a small a. And if they could be either one, then we wouldn't say there's 26 letters. There would be 56 letters after that. Okay. So what we're going to do is say there are 26 letters to choose from. And notice that it also says repetition is permitted. That means that once you choose one of these, you can still choose it again. So we've got 26 and 26. Now for the digits, remember there's 10 digits, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. So we would have 10 digits to choose from, right? And then because repetition is permitted, we're going to then say that you would just have 10, 10, and 10, right? And then all we got to do is multiply these out. 26 times 26 is 676, and then we'll have 4 zeros on the end. 676 with 4 zeros. You could do that on the calculator, but this should be right. So in this case, there are 6,760,000 passwords. Now in the grand scheme of passwords, that is very, very small amount. I mean, I couldn't guess them all, but you could write a computer script pretty quickly to go through a brute force hack and do some password guessing. It'd be relatively easy. That's why a lot of passwords aren't just 6 characters long. And a lot of them make you use a capital and a small case letter. And so you don't actually have 26 choices. You actually have a lot more choices. It's usually closer to almost 70 choices because you have like all the capitals, all the smalls, all the digits, and then you have some of those extra signs like the exclamation point and the hashtag or the pound sign and the ampersand and question mark, all those other things. So like for instance, just to give you guys a little sneak into my life, my Wi-Fi password that's my Wi-Fi password. But so let's just say you're not going to guess it. I will tell you though that when you're making passwords, just a little piece of extra advice. When you're making passwords, a big thing now in password security is not just passwords, but rather passphrases. Like this would be really hard to remember if it was like 932AXY capital P 91 Q ampersand, like that would be really hard to remember. But if it's some easy little phrase that's important to me, like Sally sells seashells, 1993, that's not my password. That's super easy to remember. It's also really easy to tell people. So there's a little, keep that in mind. Whenever you're making up your passwords, use passphrases because it's going to extend them out, make them a lot longer and a lot harder to guess. Just don't make it a super easy passphrase like, I love you. Like that's dumb. Okay. Anyways, let's get back to this. Sorry, that's my little PSA about cybersecurity. Repetition of letters and digits is not permitted. So this time we're still going to put the same number. It's just, um, 6 characters, right? 2 letters, and then we have 4 digits, like this. And then what we're going to say is there's 26 letters for the first choice, and then because letters are not allowed to repeat, once we choose a letter for this one, maybe we choose like the letter X. Well, now that we only have 25 choices for the next one. Okay, now we go on to digits. Digits are not repeated in this particular scheme. So we have 10 choices for the first one, but then once you use a digit, you can't use that digit again. So that means you only have 9 choices for the next one, and then 8, and then 7. Okay, so let's go ahead and do this. We'll do 26 times 25 times 10 times 9 times 8 9, 8, oops, times 7. Okay. Notice that just by disallowing the passwords, or the repetitions, our passwords were almost cut in half. This is 3276. Okay, so by making it so that we can't repeat things, we've taken off a lot of the possibilities. Okay. Now this last one, the first letter must be a vowel and the first digit cannot be a 0. Repetition is not permitted. Oh man, we've got a lot going on here. So the first letter must be a vowel. A, E, I, O, U. We're not going to count Y. So we've got 5 choices for the first one. This one must be a vowel. Now, this next one, this is the one that actually tricks a lot of people. And if you pause the video and you got this whole problem right, good job on you. Good on you, because this is a hard problem. If you haven't, maybe go ahead and try to finish this one now. So the first letter must be a vowel. Check. It doesn't say anything at all about the second letter other than digits are not permitted. So there's actually 25 choices here. A lot of people put 21, and that's not correct. If you've put 21, then what you're thinking is that you can't use any vowels. But it doesn't say that. Let's just say you pick the letter A to be the first. You're going to make your password. You're like, okay, I want to make it A. Well, in this one, you can put any single letter except A. You could put E if you wanted. There is no restriction at all on this second letter other than it can't be a repeated value from the first one. So that's why we get 25 there. Then for digits, it says the first digit cannot be a 0. Well, that means you only have the digits 1 through 9. Okay? And then here's where it's tricky. Those are how this is going to look. Some of you are like, wait a minute, 9, where'd that other 9 come from? So we said 0 can't go here, so you have 9 choices. 1, 2, 3, 4, 5, 6, 7, 8, 9. You pick one of them to put it there. But 0 can be a choice here. So let's say you pick like the number, you make this one the number 2. Well, now, for this blank, you can pick any digit except 2, including 0. And that's why you get 9 choices for the second one there. All right, so we got 5 times 25 times 9 times 9 times 8 times 7, right? I'm going to go ahead and do that. 25. Okay, and I got 567,000 even. Okay. You start putting restrictions on there and our passwords really get cut down. All right. All right, next. There is actually a nice way of writing some of this stuff, and it saves you a little bit of time, and it's by using this exclamation point. And so when you see something like 5 exclamation point, it's not just that somebody's really excited and they're like 5. That's not what it is. This is a mathematical notation that means multiply this number all the way down to 1. like all of the digits all the way down to 1. So I'm sure that they, if you had to do this with like 50, and previously you always had to do like 50 times 49 times 48, whoops, apparently I can't write, times 47 times 46, and so on, like that would really suck. Maybe once they figured out this notation, they were really excited because they're like 50, and they get to save themselves all that time. So it is very exciting. But it's a very simple thing to do. You just have to take that number and you write them out all the way down to 1. We use this anytime you are arranging objects. Now, pretty much anytime you see the word arranged, we're going to be using this notation, right? Anytime you see something like line up, we're going to be using this notation. Anytime someone is running in a race, when they're lining up, when they're arranging things, that's when we're going to be using notation like this. And we'll be discussing something called a permutation here in just a second. Okay, a different symbol for it. Okay, how many ways can 7 children be arranged in a line? Well, we just got done saying, well, let's have all 7 children line up. We'll put 7 blanks. 7 for the first blank, 6 for the next blank, then 5, then 4, 3, 2, 1. And this is how we could have done it prior to this page. But now that we know this symbol, I could actually just do that. Like 7! And I get so excited because then I don't have to write out 7 times 6 times 5 times 4 times 3 times 2 times 1. And on your calculator, now let's go to this one. I like this one better. Like we can do, we can put all these on here and be like, well, let's do 7 times 6 times 5 times 4 times 3 times 2, oh man, times 1. Okay, got it, 5,040. But you know what? We have some other places that we can go visit on our calculator. This is a really nice calculator. It's got a lot of stuff on it. If I go in here to options, none of that looks like it's good to me, but there's a little arrow here that says let's go find some more. We're in a whole chapter called probability. Let's see what's here under probability. Whoa, look at that. Look how excited it is to show us this. It has a little x squared right here. So I could do 7, hit that button, and also get 5,040. Okay, so your calculators have buttons to do this. Now I know some of you out there use these TI calculators, so let's go ahead and we'll talk about that real quick. On the TI calculator, where that would be is first you're going to want to hit the 7, so you do 7, and then we go into math. Look, they have a probability section as well here on the TI-83. So we're going to go over to the probability section, and then right there, your number 4, that's your exclamation point. It's called a factorial. So 7 factorial, yes, it works too. Okay, so those are some calculator usages here to help you out. That does get us 5,040. Now, maybe you don't want to go all the way down. Maybe we were going to take those 7 kids and we actually only were going to line up 3 of them, right? Or, maybe we were going to take those 7 kids and we were going to only line up 5 of them. Well, then we don't want to go all the way down. That's where this notation comes in. And what it does is that this n minus r factorial is actually just going to divide out the ones you don't want. I know that seems kind of weird, but 8p4, you can write it out as 8 factorial over, and then notice here that it's n minus r, so it'll be 8 minus r 4. So 8 minus 4 factorial. That's going to be 8 factorial over 4 factorial. And let's think about what these mean. 8 factorial means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And 8p4 means if you have 8 objects and you were going to pick 4 of them to line up. Maybe if you had 8 books and you were going to pick 4 of them to arrange on a shelf, right? Well, we know when we did that last time, we said, oh, that was just 8 times 7 times 6 times 5, and we're done. Well, here on this problem, I still got to do this 4 factorial. So I have 4, 3, to 1, because factorial means go all the way down to 1. You guys learned a long time ago that whenever we have fractions, you can cancel tops and bottoms. And look, 8p4 comes out to be 8 times 7 times 6 times 5. The end. Done. Well, we got this all figured out. Now, if only there were something on our calculator that we could use for P. Oh, look at this. NPR, not National Public Radio, NPR. This is a permutation. So I could do this and say 8 NPR 4. 8 books, and I'm going to pick 4 of them to arrange on a shelf. If you think back to that problem from before, 1680. Now on the TI calculator, you actually got to do the 8 first. Then we'll go back into math, arrow over to probability, just like we were a second ago where that factorial was. But now you can see we have NPR. So we hit that, 8 NPR 4. And this will also give us 1680. You know, or let's say that we had, let's go back to that idea of those kids. What if instead of arranging all 7 of them, what if we did only want to, we were going to give candy to the first 3 kids in line, right? And maybe, you know, the order matters. So we're going to give several pieces of candy to the first kid, and then 2 pieces to the second kid, and 1 to the third kid, and none for everybody else. Well, then what you would say is there's 7 choices for the first one, then 6, then 5. 7 times 6 times 5. And that's a nice way of doing things. Or you can say 7p3. See, this is just going to be 210. Now, because 5 times 6 is 30, times 7 is 21 with a 0. Okay, but 7p3, let's go ahead and check that real quick on our calculator. 7 kids, and we're going to line up 3 of them. 7p3 is 210. Okay, let's do a little bit more practice. Why don't you grab your calculator, make sure you understand how to do these on a calculator. Probably make sure you understand how to do them by canceling out as well. It's a good idea to get into that habit. Don't just blindly punch something in a calculator and have no idea what you're doing. You know, this you could think of this, if 9 people were running a race and the first 3 people were going to get ribbons, it's 9p3. I already know that my answer is going to be 9 times 8 times 7. Right? Because if I'm picking 3 blanks, and I'll start with 9. 9 times 8 times 7. Now, according to our formula, it'll actually look like this. Right? If you plug the numbers into the formula, it looks like this. But I'm here to explain things, and I want to make sure you understand why things look like they look. Right? 9 factorial, that's 9, 8, 7, 6, 5, 4, 3, 2, 1. 6 factorial, sure, you can write it there. I always like to write it over. 6, 5, 4, 3, 2, 1. And then you know that we can cancel tops and bottoms like that. So right here you can see we're just left with 9 times 8 times 7, right? Which is what I came up with over here. It's almost just easier to do it this way. This is a nice little definition. This is what it means. But, you know, just put 3 blanks and start with 9. Up here, pick 5 blanks. Start with 10. 10, 9, 8, 7, 6. There we go. Now, of course, we can go to the calculator and do this. You know, if we do the top one here, that's going to be 10. Whoops. 10 math. Arrow over to probability. Oops. NPR 5. So 30,240, and if you just multiply these out, that's what you will get. 30,240. Don't forget your commas. That's important when you're dealing with large numbers. It just helps us to see them better. Okay, this next one, 9p3, we can actually just put in 9 NPR 3, 9p3, 504. Multiply these, you get 504. Okay, so the last thing that we're going to look at today deals with the number of unique ways. of arranging things. You see, if you were going to line people up, then all people are unique, and so of course they're all very different. But if I'm arranging some letters, we'll say, then one L is the same as another L. It doesn't matter which L I pick, and so I don't actually have all of the, tons of different choices for each blank, because if I have repeated letters, it's not unique. Okay, we've got to actually divide out the repeated things, because you see, whenever I go to pick a letter, let's say that I wanted to pick some letters for this, and I decide on, I could put any one of these. Looks like 11 letters here. I could pick any one of these 11 letters for this. The problem is that if I decide to pick an A, this A, this A, and this A are all the same. So I don't truly have the 11 different choices. Now, the easiest way to do this, though, is to treat them like they are all unique and say, let's have 11 factorial, right? Or 11p11. And then let's divide out all of the repeated permutations. I see I have 3 A's here, so I'm going to put 3 factorial on bottom. I also notice that I have 2 L's. So I'm going to put a 2 factorial on bottom because I have 2 L's. I put the 3 factorial for the 3 A's. Now I put this 2 factorial for the 2 L's. Let's see. I see 2 S's. So I better put another 2 factorial. I'm dividing out all of the repeated combinations. I see I have 2 E's, right? And so I'll put another 2 factorial down here. And those are all of the repeats. So what I need to do is multiply out 11 factorial and then divide it by this huge number. Now, there's a couple ways that you could go about doing that. I'm going to show you maybe the way that I might do it is I might say, you know what, this number down here isn't that bad. In fact, it's just going to be 48. I did that without a calculator, by the way. Okay, because I know 2 factorial is just 2. 2 times 1. 2 times 1 times 2 times 1 times 2 times 1. This is all going to be 8. And then 3 times 2 times 1 is 6. So 6 times 8 is 48. So what I really need to do is do 11 factorial divided by 48 on my calculator. Now, that's how I did this one. I know a lot of people are like, I can't do that multiplication in my head. You're crazy. Why are you doing that to me? Okay, then don't. 11 factorial divided by, this is crucial, parentheses, 3 factorial times 2 factorial. I think you don't even need to put the times. I think it'll get it on its own. I don't know, maybe we'll see that here in a second. We'll see if it does. Times 2 factorial, close parentheses. See, when I do divided, this is what's going to put all of this down here on bottom. People that do this wrong often forget to put this in parentheses. Then all it does is it takes the 11 factorial and divides it by 3 factorial, and doesn't divide it by anything else. So you want all that to be in bottom. And that's where we get our 831,600. Now the next thing we're going to do is I'm going to go back and double check that. And let's see if we can. There we go. Let's go back and take these out. I'm curious to know. Obviously, I could check this off screen, but now you're with me. We're already this far. We're going to keep going. Yeah, see, it doesn't like that. So that's what you got to put the multiplication things in, and then same idea on the TI. So it's the same thing. You got to put the times in, times, times, times. And that's how we get our answer then. All right. Okay. Why don't you? Can you think of any other words that have a lot of repeated letters? Okay, let's all say it out loud. Say the one that you're thinking of out loud, and then maybe Maybe I'll pick the one you said. You can think of any other place that have a lot of repeated letters that make this interesting. Okay, well, I think I heard one of you say Mississippi. Too bad. I'm going to save Mississippi for an assignment or a test. Who knows? We're going to do the word bookkeeper. So I'm going to first go through and count up all the letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I know that I'm going to have 10 factorial on top. Now I got to go through and identify all the repeated ones. Well, just start off. I see 2 O's. Okay, so 2 factorial for the O's. That goes on bottom. Then I notice that we've got 2 K's. So I'll put 2 K's down there. All right, seems pretty reasonable. And now I can see that we also have 2 E's and 1 more E. That makes 3 E's. Why did I put 2K? 3 factorial. There we go. And then I think that's all the repeated letters, right? We have a B, we have a P, we have an R. All right, there we go. That's it. 10 factorial over 2 factorial, 2 factorial, 3 factorial. So let's do 10 factorial divided by parentheses. Again, here's one where I just do it in my head. It's going to be 24. But, you know, let's go ahead and put it in here so that you get some practice. 2 factorial times 2 factorial times 3 factorial. Okay. And then hopefully you got 151,200. That's how many ways, distinguishable permutations, there are for the word bookkeeper. All right. Well, I hope this was helpful to you. I hope that you learned something about permutations, and we'll come back and look at something called combinations. Permutations are when order matters. Remember, a big thing with these was arranging or lining up, right? So we'll look at what happens whenever the order doesn't matter in the next lesson. All right, good luck as you work on permutations.